Okay, hello people. This is the second week and lecture one, and on the agenda today there is a problem which deals with the chapter four of the textbook. It's rotating this problem, and I'll talk about these items two and three in a minute. So basically, we have a disk or a disk with a hole in the middle that's somehow rotating in space. And let's not worry about how this is actually done. Let's pretend that it's rotating. Generally speaking, something like that. There's a shaft through it, and the shaft is turning, and therefore make the disk turn. But pretend that this is a UFO is turning by itself. Now, it's one of those problems at a constant speed, by the way. What we want to know is the stress distribution in this disk, and it's one of the few problems that can be actually solved analytically. And we're not worried how this derivation is done. The dimensions of the disk are given on the top. It's assumed top left corner. It's assuming that it is made out of steel, and the constant speed is uh, taking place. Now, uh, the hoop stress. There are three stresses that are critical here, very important to identify the problem. One is the hoop stress, which means around the disk, tangential stress. The other one is radial stress, and finally the axial stress. Now, the axial stress is zero if there is no obstruction or there is no restraint in the axial direction. Hoop stress and radial stresses are plotted here. The dashed one is the radial stress. So basically, it's zero in the middle, at the hole in the middle, and then zero on the outside. And there's a maximum value that it achieves. So this dashed curve is the radial stress. The hoop stress is never zero, biggest on the inside, and of course it drops down, but it never goes to zero on the outside. This problem has many planes of symmetry. In fact, infinite number of planes of symmetry. For example, one thing that's obvious, you take a cut through halfway through the thickness of the disk, half of it above, half of it below. That's obvious. But the other ones that are not maybe that obvious is that you can take any cuts like that, and the sector, let's hypothetically say this is a, I don't know, 45-degree sector. The one next to it, the next 45-degree sector looks exactly like that as far as the stress distribution and displacement, etc. Therefore, what we're going to do is first I solve the problem where I take three cuts, two cuts at 45-degree angle like that, and one through the middle, and then I come back and uh, eliminate that middle plane cut and see where it takes us. And one other thing that I want to point out too is that there's a mention here: use surface slider or user-defined restraint. Let's Let me completely ignore the second part of this, and then I come back and uh, explain to you what if I didn't want to use surface slider and instead I wanted to basically force meaning impose the roller condition using the item that we call user defined. All right, so let's go ahead and make this. When it comes to creating this disk, 45-degree sector of the disk, there are two ways you can do it. There are many ways, but one of them is uh, draw the circle and then pat it up, or a sector padded up. The alternative is draw a rectangle and shaft it. And that's the route that I'm going to go today. Okay. So let me go here, start with the part file, and immediately I'm going to save it. So file, save management, save as. Uh, yeah, I'm going to make a folder here, and I'm going to call it my rotating disk. And I'm going to put that stuff in this folder. Okay. So on the vertical plane, I will sketch. Remember, my first try is uh, just take half of the thickness. So I'm going to draw a rectangle like so. and I'm going to put some dimensions. So where's the dimensions here? The distance from there to there is 1 inch. That's the inside radius of the whole of the inside, or the radius of the inside hole. And the dimension from here to here is 6 inches. That's the outside radius. And the height is half the thickness, 0.5. Okay, good. So we exit. And now instead of doing any padding, I do you see that? Here it says shaft. You click on the shaft. It says, where is the sketch? This is the sketch. And where is the axis? The axis, you can do right click about the Z axis. And then we're going to go by 45 degrees. 45. I took a 45-degree sector. You could have done 30 degrees, 5 degrees, 10. Okay, doesn't matter. Now, uh, that's pretty much it. Let's apply material to this thing as far as geometry goes. So we're going to select the metal, steel on that part. And then we say, okay, good. In the event that you want to see the properties of the steel, double click on this, select the analysis tab. These are the numbers that you see, Young's modulus, Poisson ratio, etc. We're using the default properties, so that's fine. Now click on the floppy so that everything is saved. Good. Now we're going to go to analysis and simulation, generative structure analysis. And let me change the rendering here. There we are. If you want to see the mesh, is right click, put the cursor on nodes and element, right click visualization. There we are. Okay. But if we want to know the type of the elements, double click on this. It tells you that it's parabolic right there, and the size is not much. So when you think about it, this problem, based on the information that's given here, has a high stress concentration around the inside hole. You can see that the stress shoots to a large value very rapidly. That means you need a finer mesh in this area, and this is the critical area for our problem. Therefore, let me do a mesh refinement here. First, deactivate this so that it's not stopping me from doing the rest of the stuff. Let me remind you that in the tool model manager, the second icon is made of these three possibilities, three icons, and this one is the local mesh size. So you click on it, and it says where. So I want there, and I want a size. Let me see now. Let me make this thing 0.1. See how it looks like. In fact, if you zoom in, you can see it's sitting right there. If it's too big or too small, etc., you can make the appropriate changes. That's fine. Right click, activate, and it's going to be a finer mesh in this area. You can see that. Okay, very good. So let me now deactivate this and proceed with the rest of the problem. First, I'm going to use surface slider completely. So let me click on the surface slider here, there, and there, and the bottom. So, okay. All right. I'm going to move these things up here so that we have more room. Okay, good, good. Now, when it comes to the load, let's see now. We're talking about a centrifugal load, right? This is rotating, and therefore it's extends, stretches axially outward, and obviously shrinks in the thickness direction. So basically, we are dealing with a rotational motion. The question is, which one of these will take care of rotational motion? First of all, this is a pressure, that's a force, this is gravity or acceleration, actually. There is the enforced displacement that we have done. The question is, where is that rotational thingy? Let me remind you that if you have a ball and attach your string to it and start rotating this string so that the ball goes with it, Even at a constant speed, you might say, wait a minute, if it's constant speed, there is no acceleration. But you know from your dynamics class that if an object goes around a circular path or around a curved path, there is always an acceleration, inward acceleration, which is called radial acceleration. So in fact, if you look at this thing, which has the kind of acceleration icon, if you expand it, you see that there's two things in there. One of them is linear acceleration. We have already handled that. This says rotational force, which means exactly what you want. You click on it, and it asks you for a couple of things. First of all, it says to what? The support. If I select anything here, the whole part is selected because this is a body force. Okay, the whole thing is selected. And it says, where is the rotation axis? Well, I need an axis about which this is rotating. And unfortunately, I cannot select, I don't have a line here. The line must be, and I don't have a line here, and I don't have, basically I cannot select, say, Z axis from the menu. By the way, let me change this thing to 0. Okay, very good. So the question is, how do I do that? Cancel that? Either you go to the part, make a line here and use it for that purpose, or go back to the part and instead of making a line, create an axis system right there and use its Z direction as the axis of rotation. So let's go to the part. How do we do this? One way is to expand this, double click on the part. It sends you to part design, and you can see that there is a toolbar here which actually says tools. This is kind of at the bottom of the utility toolbar, and there is an icon here that looks like an axis. It's axis system. As soon as you click on this, it's going to create a axis system at the global origin. Notice that this is where the global origin is. If I click on that, immediately it made an axis system for me here. And I want to use its Z direction for that purpose. We say, okay. So it created an axis system. Here you can see that axis system 1. All right. And then I'm done with the part. So let me save this thing before I go anywhere else. Now we go back to the finite element module. You can double click on anything below that. It'll send you there. Notice that I am in there. And now we click on that rotational force, select this, and for the axis system, for rotation axis, you can go and select this Z. You see that? I can pick it. I can pick it. And as soon as you do that, it puts the icon that looks like rotation about something, about that line. And then you put down the value 1000 RPM because here where is this? It says the 1000 RPM. If you want, you can type 113 rad per second and it converts it into 1000 RPM, very close to 1000 RPM. But that's because my default units in the tools, options, parameters and unit is set to RPM. If you don't like that, you can either type 113 rad underscore S or go and change your default unit to something else. Now, as far as the angular acceleration is concerned, it's 0 because we're assuming that this is going at a constant speed. And I say, okay, very good. The analysis file has not been saved, so let's go ahead and do that. File, save management. The part was saved. Analysis was not saved, so I'm going to say uh, this analysis, save as, in that folder, which is called my rotating disk, put it in there. And I want to remind you on the exam for marking purposes, you have to give me for this problem both the part and the analysis. One of them is missing, I can't mark it for you. All right, so let's go ahead and compute. Compute means run it basically. That's fine. This is the warning about that surface slider. That's it, done. So what happened? Let me close this. Okay, so what happens? Well, the disk will go outward and shrink sideways or lengthwise. So let's look at the deformation first. You click on this. There we are. And if you animate it, you see that actually it goes outward. You can see that. Very good. If you look at the stress distribution, you click on the, well, first of all, if you want the displacement, you click on it and change this to average ISO and change the material to change rendering to material shading. Looks like that. Biggest displacement on the outside. But this is a very small displacement because after all, this is not gum. 1 inch piece of steel rotating at 1000 RPM. That's nothing. And then let's look at the von Mises stress. There we are. Von Mises stress. Now notice that the value, the biggest stress is in the middle, 239. And if you go to this particular analytical solution, it's also around 200 and, well, it's around, I mean, theoretically, it should be around average of these two, maybe 200 and, uh, uh, what do you add these two, 275-ish? Okay. So obviously, it's not that, but it's not matching theoretical results either. So anyway, I'm not concerned about that. It's close enough for us. The other thing is that uh, if you click on this icon here, see this? This is displacement, right? But it's got other stuff that you can show. Among them, principal stresses. You click on it. Remember from your stress analysis class, you can see that at every point you have three principal directions. The numbers are written here. For example, if you go there to this very, oh, it's kind of hard to see it here, hanging there, right there. Let me go to this one of these corner points. Select one of these. It shows you two numbers, three numbers actually. One of them is the radial stress. The other one is the axial stress. This must be the radial stress. The and one which is the hoop stress. So let me see. This must be the hoop stress. See, 239, 239. Both the other two are both zero. Okay. What I'm saying is that you can actually plot the hoop stress by itself, not the von Mises stress. So I plotted the principal stresses, and you double click on it if you want a different rendering, and there we are. So this is the value of the uh, uh here. Move this thing there. This is the biggest principal stress, which happens to be the hoop stress. Okay. Right there. It didn't change at all because on this surface, radial stress is zero, axial stress is zero, so the hoop stress is actually one meter stress. Okay. Now, I'm going to save this. Okay. What I want to do is repeat the same problem, but not use any planes of symmetry. Okay. Not use any planes of symmetry. So that being the case, let me actually uh, close this. I go back to my part. I go back to my part, and instead of padding it by, oh, sorry, instead of that rectangle being half height of either zero 0.5, there's two ways you can do it. You can go to that sketch. You can go to the sketch and make this thing one. That's one way of doing it. The other one, if I'm too lazy to do it, what I can do is I can say, okay, why don't you mirror this piece with respect to that top plane? Let me do that. Because you already know how to change the dimension. Here's the mirror. Mirror, mirroring element is this, and the current solid is that. So there we are. I could have done this by going to the sketch, making the height one. I understand that, but this is the other way of doing it. Okay, so let me save this thing. Now we're going to go to, once again, to analysis and simulation, generative structure analysis. I'm doing this thing from the beginning. We could have salvaged some of the stuff that was done, but it's shooting us, maybe shooting ourselves in the foot by, trying to fix that other analysis. Not fixing it, but changing it. Okay, good. What do we know? Surface slider here and there, but not, oops, cancel that. not two faces. Cancel. Let's try it again. Surface slider on this, turn around and that. Okay, very good. Just like before, except that I'm not going to put a surface slider here because this is not the plane of symmetry anymore. All right. Now, rotational axis, rotational force right there. Going through the steps again. The support is that piece. The axis of rotation is that Z axis. You can see that right there. Yeah. And the angular velocity is 1000 turn per minute, RPM. And angular acceleration is 0 because it's going at a constant speed. Okay. Let me save the analysis. File, save management. There's the analysis, save as. In that folder, it already have something which is analysis one. So I'll say analysis one, but change the name of it so that no symmetry, no, okay, symmetry, no third surface slider, SS, surface slider. Okay, good. Okay. Everything seems to be all right, except that when we run it, it's going to bomb out. We'll see. Run it. Ignore that warning message. Say yes, and watch it bomb out. There. So it says I couldn't do it because maybe there is not enough restraint. And in fact, you can see that this whole thing can move as a rigid body up and down. You can see that because there's a surface slider here, a surface slider there, up and down can go. Before, in the first run that I made, the middle of this was a surface slider. It could not go up and down, but here it does. So basically, we have to remove the rigid body motion. Now, if you're not sure why it happened, you still can plot the deformation and displacement. Let me plot the displacement for you. It looks like that. And if you animate it, you can see what happened. Okay. We say okay. And we deactivate the spot because we want to solve the problem. Fix the problem. Deactivate. So to take the rigid body motion away, I take one point and say, hey, you cannot go up and down. It doesn't matter which one of these points I take. So I'm going to go to user defined. See that? Remember this? Clamp surface slider user defined. You select one point, for example, this point, and say you cannot go up and down in the direction 3. Generally speaking, if you haven't done anything, these are not checked, but check that. Now remember, these three restraint about rotation has no bearing on our tetrahedral elements. They will come in the beam element and shell elements in a few days. Say okay? Now when I run it, that rigid body motion should go away. It should run. No, and no error messages. Very good. So let's look at the deformation or displacement. There we are. Can I animate it? Yes. But nothing is moving. And we went through this thing last Friday. I said that that's because previously you asked Katia, you interrogated Katia to tell you what the issue was. And because it was going all the way to infinity, essentially, it had to reduce the scale. So what you need to do, if you want to see this thing moving, go back to this icon, so important, right there. See that? Analysis tool, right there, amplification factor. It reduced the scale factor to that. We don't want it. Say default. There. And now when you animate it, it's actually doing what it is. Okay, these are of course displacement. So if you look at let me double click on that, average ISO. Let me also change the rendering here to material. Let's plot the von Mises stress, and it should be very close, almost the same as what we had before. Almost, not quite. You can see that. It was 239, now it is 242. Very good. So that takes care of this problem. Okay, now, what is this business of use surface slider or user defined restraint? So let me go through this thing through the same example, except that I'm going to kill this. But first of all, let me save this. and close that. All right. So we have the full model right there. You're looking at it. Now this access system I created here because I wanted a line or the direction here so that I can say this is rotating about that axis. That's fine. So up to this point, no problem. Now let me go ahead back to, this is the third time essentially I'm doing the problem. Let me go ahead back to analysis and simulation and generative structure analysis. Say, okay, change the rendering here. Very good. Now, I don't want to use the surface slider. So how does this look like? What if I don't have a surface slider here? The other way of saying that is it, I don't want to use the surface slider. What the surface slider says, nothing moves perpendicular to that face. Well, no problem. I can go and click on the user define, select that face, and say nothing moves perpendicular to it, which is direction 2. We can see that. Y-axis. Say good. I want to say the same thing on this one. So user define on this face, nothing. The problem is that this is at an angle, 45-degree angle. It's neither, the normal to it is neither X nor Y nor Z. So the question is, how do I do that? If I insist on not using the surface slider and I want to use this, how do I say that things on that plane do not move perpendicular to it? So let me cancel that. Let's go and create a coordinate system here, axis system here, which is aligned with, for example, normal to this plane. How do we do that? Remember, coordinate system cannot be done here. You have to go back to the part. So let's go to the part. Now we're in part. And do you remember how we created this axis system? We found the tools toolbar right here, and there's an axis there. You can see axis system. Now, it's going to try to do another one right at the global origin, but I don't want my origin to be there. I want my origin, for example, to be at this point for visual purposes. And I want one of these directions, X, Y, Z, to be aligned with, for example, this line. For example, notice that it says X, Y axis, X, Y, Z axis. Let's say the X axis, I want it to be aligned with this. So it's going to take X axis and put it on that line. Just watch to this. Excuse me, just watch this coordinate system. When I select this as the x-axis, look at what it did. It said x is along that, and therefore z is going to be perpendicular to it. So now we have a direction. So, by the way, you can call this thing anything you want. You can give it a name. Right now is just axis system. Yeah, you can call this thing anything you want. So we say, okay. Now we have two of them. This is the one that was created. So we're done there. We go back to the analysis, and now user defined, but not the global one. You see that? Not the global one. You change that to user. It says, okay, go pick it. Well, I can pick it from the screen, for example. This is access system 2. You can see that. And for that system, nothing perpendicular to this direction. Again, direction 3. Direction 3 in this case, okay? And says where. Okay, support is that corner point. For example, this corner point. It doesn't matter. That corner point, or this corner point, or this corner point. It makes no difference. We say, okay, good. All right. So this is, I'm not using any surface slider. Oh, I'm sorry. I made a big mistake here. I didn't want this one. I want the whole face. Oh, okay. So double click on that. Not this point. You can say remove support. I want all points there not to move, not that, only that point. Good. So let me save this thing. File, say management, analysis, save as. I'm going to call it Well, I think we already saved. Oh, yeah, this was a surface slider. So I can call this thing, I call it, I'll call it, uh, no, uh, uh, no surface slider. How about that? Yeah. Good, good. Now, if you run it, it's going to bomb out because this is still too free to move as a rigid body. But let's check it out. So we click on that, run it. Okay. It's going to bomb out. Again, because it can move as a rigid body. You can see that there. So we fix it, just like we did before. Right click, deactivate this plot. So we do another, we can take another point and say, hey, you cannot move in the direction, vertical direction. So user define any point, any vertex. Now here you have to be a little bit careful. Right now, the user is active. If you want global, say nothing moves, or that one point does not move in the global Z. You see that? If you say global, you better check Z. Okay. But if you had user, this one, if you had user, and that's what you had, you say the point that I picked, which happens to be one vertex, I remember which one it was. Maybe it was on this side. If I don't remember, let me remove this and select it again. Oh yeah, it was that point. Well, first of all, it's asking for coordinate system. Oh, the support is this point, for example. The coordinate system is user. If you're using user, notice that upward is Y. So it's not this guy, but it's this. If you're using global, it would have been third. So just be careful because it just happened that user was active. And if our user is active, this point cannot go in the vertical direction of the, which means that Y in that coordinate system. Okay, so fine, run it, and it's going to work fine, no problem. You'll see, very good. And if you activate this thing, okay, I think I forgot to put the load on it. Okay, so let's deactivate that. I completely forgot to specify the load. No wonder it gave me 0. So you go to, where is that? Rotational force. The support is that part. The access system is, just be careful. Access is this direction here, this direction, 1000 RPM. You say okay and run it. What we got before was not wrong because it was not turning. Finished. Let's look at the displacement, for example, and you can animate it. If it doesn't move, that's because we just interrogated it. Okay, so we say, no problem. Give me the default scale. Right, there we are. And now you can animate it. Obviously, it does the same thing. So this means that I use the surface slider. This means I purposely avoided using surface slider. And I showed you how to create a local coordinate or user-defined coordinate system and how to use it, etc. Okay, I mean, nobody stops you from using surface slider. It's just that I wanted to show you some other things that can be done. All right, folks. So starting next week, we're going to be next no, not next week, next lecture on Thursday. I'm going to start using beam elements. All right. Good luck.